All right, so last class we were talking about transformation, and we talked about the couple of, the quadratic model, including the higher order term model in the model, and using square root transformation. Remember the major benefit of using square root transformation was it can correct heteroscedasticity problem, right? When we have residual plot goes like that, right? When you take a square root transformation, right? Then we could make it this way, right? Make it a random distribution of residuals from this some clear pattern, right? The residual plot with the pattern. Okay? Okay, so let's continue. Let's talk about one more type of transformation today. It's called the log transformation. Okay? And I remember I was trying to explain the concept of production function. Just one second. I feel it's a little... Okay. All right. So, yeah, and I spent a few minutes talking about my experience, work experience. Yeah. All right. So, production function. You know what the production function is, and the major role of log transformation is we use when we have multiplicative model instead of additive model, right? So multiplicative model is like this. Instead of beta naught plus beta 1 x1 plus error term, right? We have everything multiplied here, especially the beta 1 is the exponent of x1, right? Instead of it's a coefficient in front of multiplied in front of x1, right? So if you take a log of both sides, right, then it becomes log y1 becomes log beta naught plus beta 1 times log x1 plus log error, right? So in a sense, we are converting multiplicative model into an additive model, right? And then that way we can run the regression, right? So when you have the x1 variable, instead of running regression with y and x, you're running regression with log of y and log of x, right? Then we can get that result, estimate the regression equation. Okay? All right, so let me give you a few examples of this. And for that purpose, let's see. There's what we call log linear demand function or demand curve. Okay? And, well, you know what demand curve is in principles of economics. I'm sure you have learned the typical shape of demand curve. Okay? And price goes here and quantity goes here, right? And the demand curve shows there's an inverse relationship between price and quantity demanded, right? When the price rises, then quantity demanded would go down. Okay? That's the idea. Sometimes in economics, we try to actually estimate the actual demand function. And, well, the typical, well, because it's not a straight line, I mean, I'm sure, right, in simple, I mean, principles of economics, well, perhaps in the beginning, maybe they use the straight line demand curve, right? But many times we use this curvilinear demand curve, curvilinear shape of demand curve, because it's closer to reality, right? So how do we define, or how do we come up with this functional form for demand curve, right? Many times we use Q equals beta naught times P to the power of beta 1, right? Multiplied by M beta 2 and error term, right? We can specify it this way, right? Well, Q is, of course, quantity demanded, okay? P is price, okay? M, any idea? What would M stand for? What? Money? What money? Income. That's right. That's right. Right. So if you remember, we consider, of course, quantity demanded is affected by the price, but it is also affected by what? Consumers' income, right? You remember income effect, right? Right. So, I guess this, and in I'm sorry, I'm a little bit too hasty here. I'm trying to explain so many things today. Right? In reality, you can include many other variables. If you get into the managerial economics, right? You're trying to come up with your quantity demanded for your particular product, right? Then, of course, price matters. But there is another price that can matter, right? If there is a substitute for your product, right? Or complement for your product, right? Then the price of other things will also affect this the quantity demanded. And what about advertisement, right? How much money you spend in advertisement, right, for your product, right? That can also influence quantity demanded, right? So actually, this can be quite lengthy, right? Price of own price of your competitive product, income, advertisement, and so on, right? All right, so let's just make it simple here, right? So in this case, if you take a log, then you're going to have log Q is log beta naught plus beta 1 log of P plus beta 2 log of M plus log of epsilon or error, right? Okay? Okay. And here, you're trying to find the effect of price. You're trying to interpret this beta 1. What does beta 1 stand for? What does that tell us? Right? So once you estimate that, estimating is pretty simple. I mean, you have the data on quantity and price and the income, right? So you simply take the log of all the variables and just run the regression, right? And you will get all this estimate, right? But in that case, what will be the interpretation of this beta 1 coefficient or B1 estimate? Okay? Well, that's going to be partial of log Q with respect to P, or log P actually. Okay? If you remember, if y is b0 plus b1x, if you come out that way, right? What is b1? b1 is dy dx, right? because y is a function of only one independent variable, right? You can take the derivative, right? And b1 is dy dx. Okay? Is that correct? Right? Well, in this case, q is a function of p, but there's another independent variable m here, right? So you have to take the partial derivative. Is it called 부분 미분? Right? Partial derivative. Okay? So once you estimate the equation, b1 will be partial of log q with respect to log p, right? And in principles of economics, I'm sure you have learned the concept of price elasticity of demand. We typically write epsilon p, price elasticity of demand, right? And the concept is percentage change in quantity demanded over percentage change in P, right? 수요 탄력성, right? Just in case. Okay? Price elasticity of demand. Okay? How do we measure that? Well, the percentage change is change in quantity over initial quantity times 100. Okay? The whole thing divided by change in price over initial price times 100. Right? Percentage quantity, percentage price, right? Change in price. And of course, they go, right? And this comes out to be change in quantity over change in P times P over Q, right? That's how you would calculate the price elasticity of demand. Okay? Well, here, in order to rearrange or find the actual expression for that, right, we have to remember, okay, how would I? If fx is log of x, let's say simply log of x, right? F prime x, which is d fx dx, is 1 over x times dx, right? Again, I apologize for using calculus in this class, okay? But this is simple, I mean, as far as log is concerned, there's a simple rule, right? So, in other words, d log x is simply 1 divided by x times dx. Right? I guess some of you have learned this and you still remember this, right? So, if you apply that to this expression, okay, we come up with partial of log q will be 1 over q dq, right? The whole thing divided by 1 over p dp, right? And then it comes out to be partial. Okay? So partial q over partial p, p over q. Okay? And again, this dq or partial q represents a very small, minute change in quantity, right? Very small increase in, or decrease in q. Right? dp or partial p means very small change in price. right? Like 1% change in price, 1% change in quantity, right? So we come up with this expression. If you compare that, you find out that that's exactly the same expression as the price elasticity of demand, right? So what's the story here? We have demand function here. So this is supposed to be the equation of this demand curve, right? And again, maybe I mentioned it once before, right? The typical convention is when we draw the demand curve, we put the price on the vertical axis and the Q on the horizontal axis, right? But if you look at this equation, Q is actually the dependent variable, right? And price is an independent variable, right? So actually, we're talking about this relationship. Okay? Q is the dependent variable and price is independent variable, right? It doesn't really matter because we're talking about the relationship between price and quantity, right? And even if you flip upside down or, when you flip the axis, you will get similar curve. You will see similar curve, right? So this is more conceptual expression of the demand function, right? And if you really have to draw it this way, right, then you can simply convert it. You can simply rearrange once you find this equation, something like, let's say, okay, do I have, okay, yeah, you can simply flip and rearrange so that you will have price on the left-hand side, okay? In managerial economics, we, use that as an example, right? So anyway, the point here is, when you have multiplicative model like this, you can convert it into additive model by taking log of both sides, right? Then the interpretation of the coefficient becomes elasticity. Elasticity. Okay? In other words, so let's say this comes out to be 0.56. Suppose you ran the regression, right? And B1 hat came out to be 0.56, right? Can someone try to interpret that? What does that mean? If coefficient estimate came out to be 0.56. Here's the hint. Definition or concept of elasticity is percentage change in quantity demanded divided by percentage change in price, right? And that came out to be 0.56.
For every dollar increase.
Not every dollar. Here.
For 1% change in price, the quantity demanded, the percentage change of the quantity demanded is 0.56.
Yeah, actually, yeah. So I should have said negative 0.56.
So there's the inverse relationship.
Right, right. So in reality, you will get negative coefficient here, right? Negative 0.56, right? So what that means is for 1% increase in price, right, you would see 0.56% decline in quantity demanded. Okay? 1% increase in price, right? You will see a 0.56% decrease in quantity demanded. Right? Does it make sense? Okay. So that was our first example of this quantitative model, how to transform quantitative model by taking log, right, of both sides. Okay? Then that's what we call log-log equation, right? I have uploaded 2 documents on the website yesterday, okay? And the first one is this one, okay? Coefficient interpretation as basically this one gives you how to interpret the coefficient estimation in the log equation, okay? And here 1.2 gives you the log-log case, okay? And here they use the example of wage equation. WI is wage, okay? And education. This is basically what I've been using in this class, right? The education, I use the schooling, right? Number of years of schooling, age, experience, and community volunteer variable, so they included something else, right? But anyway, if you do that, right, what happens when you estimate the regression equation, right? So here, this particular variable, COMM, is logged, okay? So what is the interpretation of beta 4? They're trying to find out, right? And eventually they come up with this equation, right, which is the same thing as this expression, right? So you come up with this, but eventually that becomes that, right? Right? So here, 1% increase in community volunteer hours per week is associated 1.2% increase in hourly wages, right? Because this coefficient is 1.2, right? So that means if this variable, COMM, increases by 1%, right, your dependent variable wage goes up by 1.2%, right? Make sure you understand that. So it's the idea of elasticity. Yeah? All right. If you look at the slide here, I said, for example, Cobb-Douglas production function. That's another very important tool and concept in economics. Yeah? Cobb and Douglas, these are 2 last names. Charles Cobb and Paul Douglas came up with this production function. And obviously both are economists, American economists. And Paul Douglas later became a senator in the United States. Yeah? And many years ago, almost, 85 years ago, right? They came up with the Cobb-Douglas production function. Okay? The functional form of Cobb-Douglas production function last class I gave you the concept of production function, right? Production function relates output to different inputs, right? Of course, there can be many different inputs, right? Think about production of, say, computer or your smartphone, right? How many different inputs does it require to produce that little smartphone, right? Well, you see plastic, glass, and inside this little thing there are many components, right? The chips and the circuit board and all kinds of, that even includes a motor, vibration, right? That means that there's a motor inside, okay? And of course, there should be labor. Someone has to put together, right? All kinds of inputs, right? In economics, we simplify all those inputs into L and K, right? put all those inputs into two categories, labor and capital, right? Why we use K for capital? German, I'm sure German guys here are glad to hear that, right? Yeah. Well, the reason that I can give you is because we use C for cost, right? Well, then why K? Well, there's a famous book called Das Kapital, right? Das Kapital by Marx, right? Well, until about 20 years ago in the United States, right, they never mentioned this book in economics class. Because you probably know during the 60s, 70s, there was a very strong anti-communist sentiment in the United States, right? And of course, it was the same in Korea as well, right? I mean, it's still going on right now in Korea, right? If you say something against the government, you can easily be branded as a communist, right? Just, kind of helping, the North Korea communist government, right? Anyway, so even in the country like the United States, because of this anti-communist sentiment, this book was never mentioned and never taught, right? But in most of the European countries, I think this was considered one of the required reading for economic student, right? You know what this is in Korean? 자본론, right? 자본론, right? And I think one of the professors here teaches this, right? Okay. Anyway, so this is a very important book in economics, right? So I guess we use K from that. That's capital in English, okay? So anyway, so we use labor and capital, right? And labor is labor, simple human labor. There's only one kind, right? All the rest, whether it's money, equipment, material, or whatever, yeah, is included in capital. Okay? So many years ago, about almost 90 years ago, these two economists, Charles Cobb and Paul Douglas, tried to come up with the actual form. This is a very primitive conceptual relationship between output and input, right? But can we find the actual functional form between these variables, how they are related, inputs and output are related, right? And they came up with this expression, y is a times L to the power of alpha times k to the power of 1 minus alpha. All right? And y represents output. Well, why not q? Why we use y, right? Well, in microeconomics, we use q for output, right? In macroeconomics, we use y for output. Matter of fact, in macroeconomics, y represents many things. Output, input, output, income, what else? Output and income. What, anything else? What? Total demand. Yeah, okay, you can say that, right? Because in macroeconomics, we have circular diagram, right? We have everything has to be equal, right? Total output has to be equal to total income. Okay? In other words, GDP simply, right, is the measure of total output, right? But so you can measure the GDP in two different ways, right? You can measure it by adding up all the outputs produced, right? Or you can measure the GDP by adding up all the incomes received by the people in the society, in the economy, right? So ultimately, the total output has to be equal to total income, right? So that's why we use Y for both, right? All right, so that's the output. That's the, you can say, technology parameter, right? That's a kind of constant that represents the level of technology in the society, in the economy, right? L is, of course, labor input. K is capital input, right? What is alpha and 1 minus alpha? Well, those are elasticities, right? So how does it work? Let's see. Okay? So if you take a log of both sides, you come up with log of y equals log of a plus alpha times log of L plus 1 minus alpha times log of K. Okay? Yeah. So using the actual national income and the GDP data, right? Cobb and Douglas actually tried to estimate this equation, right? They used the GDP as the total output, right? And total amount of labor input and capital input, right? And try to estimate these unknown parameters, right? So when you do that, what happens? So let's try to think about this alpha, right? What will be the alpha? Right? Again, alpha will be the partial of log y with respect to log of L. Okay? Okay? And using, again, the d log x is 1 over x dx, right? Using that rule, right? This is going to be 1 over y dy over 1 over L dl. Okay? So you come up with the dy dl L over y. Okay? So that's exactly the elasticity, just like here. Right? What can you call this? If this is price elasticity of demand, price elasticity of demand, I mean Q is the quantity demanded, right? So what is this? What's the concept of this? Labor elasticity of output, right? Labor elasticity of output, right? You can call it labor elasticity of output, right? And what is the meaning? What does it measure? Price elasticity of price elasticity of demand, right? Measures what happens to the quantity demanded when price increases by 1%. Okay? So what does this measure?
Percentage change in output over percentage change in labor.
Right, that's right? So that's percentage change in Y over percentage change in L. In other words, their actual estimate came up this way. When they estimated this equation, log of y hat came out to be 1.17 plus 0.38 log L plus 0.603 log K. Wait a minute. Actually this is reversed, right? K is an L, right? So you can do it either way, but the way they did it was this was K, this was L, right? So this is K and L, right? So that's well, this doesn't matter, right? This is still true. You can either do it 1 minus alpha, whatever, right? Or alpha would be partial of log y with respect to the log k, right? Anyway, so they came up with 0.38 and 0.603 here. Well, notice if you add them up, alpha and 1 minus alpha, it has to be 1, right? But when they run the regression, they treated this and this separately. They used the actual amount of capital and actual amount of labor, right? They used, okay? So in the estimate, these two numbers do not exactly add up to 1. Yeah, roughly, I guess if you add up, it's about, 0.98, right? Something like that. Something close to 1, right? But anyway, so if you come up with a 0.38 for log, the coefficient of log k, right? What can you say? How do you interpret this number, 0.38? What is the interpretation of 0.38? 0.38%, right? Right. Again, remember the coefficient here is an elasticity, right? So we're talking about percent over percent, right? So what that means is if capital input increases by 1%, right? The total output in the economy, right, increases by 0.38%. Right? If the labor increases by 1%, then the total output in the economy increases by about 0.6%. Okay? So in principles of macroeconomics, in the beginning, I'm sure you learned there's 4 resources, right? What are those major primary resources in the economy? Do you remember? What are the economic resources? Land. Huh? Don't remember anything? Land, capital, labor, and what's the last thing? Huh? Entrepreneurial skill, right? Entrepreneurial skill, right? That's the typical way we classify all the resources in most of the textbook. Depending on which textbook you use, they might do it slightly different way. But land, labor, capital, entrepreneurial skill, typically we use 4 categories, right? And out of those 4 categories, we say labor is the most important resource. Why is that? Is that just because we are human? Yeah? Say human labor is the most important, right? Well, that's because when you categorize all those labor, the inputs into capital and labor, right? This is how it is, I guess, separated, right? The composition, when you decompose the total output, we find out about 60% of the output comes from the labor, right? About 40% of the output is, adheres to the capital or any other input other than labor, right? So, excuse me, that's why we consider the labor the most important input, right? All right, so make sure I gave you two examples here, the demand curve and the Cobb-Douglas production function using log-log transformation, right? And again, the most important thing is interpretation of these coefficients once you estimate the log-log equation, right? And those coefficients are elasticities, okay? All right. Let's talk about one more type of log transformation. Yeah, we don't have any more slide here, but okay, let's see. I'm going to talk about log level model, right? This is another very popular functional form used in business and economics. Okay? And let's see. The second material that I put on the web is actually the paper that I wrote with my co-author about 14 years ago. I think this was 1991 or something, right? About 14 years ago, right? And here you can read the abstract, right? Very interesting paper, and you can, I think, easily understand that abstract, right? But here, if you look at the equation, earnings equation here, right? And here the dependent variable is log of earnings. ln is natural log, right? Instead of 10-based log, right? But it doesn't really matter. You will find out that whether you use natural log or 10-based log, they work exactly the same way. So the dependent variable is log of earning, and here are all the independent variables: schooling, experience square, and gender, marital status, language, ability, the location and the occupation, and so on, right? Okay, so here, this is a typical way. When you look at this wage equation, right? Typically, they use a log level model, right? So log level means only the dependent variable is logged. Okay? Independent variables are not logged. Okay? Why do we do that? Well, so far, when I explained the regression, multiple regression, I simply used wage as a function of schooling, experience, and so on. Okay? But in reality, in real research, instead of using wage or actual earning, we typically use log of wage or log of earning. Okay? Why do we do that? Well, there's a very good reason. Okay? The reason is it has to do with heteroskedasticity, homoskedasticity, right? Because when you look at the amount of earning, let's say somebody's labor earning, right? And suppose here are different levels: low income, middle income, high income level. So you can say this is a percentile. So if you draw the graph or scattergram of, say, 1%, 2%, 3%, and so on, right? So 1% percentile means these people are the bottom, at the bottom of earnings, right? So the earnings, let's say the earnings level, earnings of the bottom 1%, right? So of course here, if this is 100, that means these are the top earners, right, in the market, right? And if you, of course, the earning will increase as you come up with from the bottom to the top, right? But it's not really linear fashion, right? The earning has kind of this log linear fashion, right? And also, if you look at the scattergram, right, it's going to look like this. So you're going to have something like this kind of pattern, right? So think about it. If you're thinking about, say, bottom 1% earner, right, what will be their average earning? Let's say something like $5,000 a year, $5,000 a year, right? And the variability will be quite small, right? When you look at the bottom level, right? The variability may be, from 4,500 to 5,500. Okay? But if you're talking about top earners here, right? It could be maybe 1 million and what? Who's the highest income earner in the world? Or maybe in the United States? Warren Buffett? Right? I don't know, maybe. Yeah, okay. His earning could be billions, which is 1,000 times $1 million, right? So you see this, the heteroscedasticity problem. The variability increases as the level of earning increases, right? So in order to correct that problem, right, we take a log of earning typically. Okay? And that's the reason, right? So what happens when you take a log of the dependent variable and use just the level numbers for independent variable? Right? So actually this is a separate, completely new model. We talked about additive model, multiplicative model, and the last thing I'm going to introduce here is exponential. Exponential model. Okay? So exponential model goes like this. Y is E, natural constant, natural number, right? To the power of beta naught plus beta 1 x1 times E, error term. Okay? So if you take a log, natural log, this time let's take a natural log because we're talking about E-based, natural constant based, okay? Log. Okay? Yeah. That becomes beta naught plus beta 1 x1. And of course, when you estimate, error term disappears. Okay? So we have log of the dependent variable, but there's no log on the right-hand side, independent variable, right? So well, running the regression is pretty simple. You just simply take the log of the dependent variable, but just use the actual value of all the independent variable and run the regression, right? But what will be the interpretation of B1? So once you estimate log of y hat is B0 plus B1 x1 B1. Well, that will be d log of y dx1, right? And again, d log y is 1 over y dy. The whole thing divided by dx. Okay. That is 1 over y dy dx. Okay. Excuse me. We can rewrite this, as this way. dy over y times 1 over dx. Right? Then what will be the interpretation here? Think about it. Can you take a look? All right, so let's say this interpretation, this number, B1, came out to be 0.24. Trying to think of what the example I was using here. Yeah, doesn't matter. Okay. What does this tell us? 0.24. You can say this is a percentage change, right? Because we're talking about dy over the actual y, change in y over the actual level of y, right? And talking about dx. Okay. So 1 unit increase in x leads to this much change in y. Okay? So we have log level. Okay? So on this side, the interpretation is exactly the same as before. For each unit increase in x1, right? We can expect this much what? Fractional change or percentage change in y. Okay? So interpretation is 1 unit in x1 will lead to 0.24% increase in y. Of course, holding other things constant, right? If it's a multiple regression. Okay? All right, so let me just look at here in this example. Let's see this output and see how we can interpret the result. Okay? So the estimated equation, log of earning, came out to be 6.18 plus 0.075. Is that schooling? No, I'm sorry, 0.07 schooling plus 0.04 experience minus 0.006 0.0006 experience squared. Okay? So, first of all, what does that tell us? 0.07. Are you a little bit confused? I think I may have caused a little bit of confusion here, right? Yeah, here. This is in this example, this was 0.24, right? In my previous example, here. So what that means is 1 unit increase in X will lead to what? 24%. 24% increase in Y, because this fraction is 0.24, right? I think you should have questioned that. I think I said 0.24%, right? But actually that's a 24% increase, right? So what about this? One unit increase in schooling, in other words, 1 additional year of schooling will lead to what? 7% increase in the person's earning, right? That's what this means. We didn't really talk about it, did we? All right. What about effect of experience? Let's say partial of log of earning with respect to experience. In other words, if a person has 1 additional year of labor market experience, what's going to happen to the person's earning? What happens when you take a partial? It's going to be, come on. Come on. What? If you take the partial of these, right? What do you get? 0.04 minus 2 times 0.0006 experience, right? Right? Okay. So, what that means is effect of experience on somebody's earning depends on that person's experience level. It's not like simple 0.04, right? What that means is if there was no term here, if it was simply 0.04, that means for 1 year, additional year of labor market experience, the earning increases by 4%, right? But that's not that simple. Here we have experience, right? So this is what I talked about. Okay? If this was simple like this, right, then we could say the earnings experience profile is a straight line. For each additional year of experience, the earning increases by 4% all the time, right? But this means we have this kind of curve, right? The actual slope, effect of experience, 1 additional year of experience on the earning, depends on where you are. Are you in 5-year experience or 15-year experience, right? Actually, because we have negative coefficient here, right? When the experience is low, it is rather steep, right? But as you increase your experience, it becomes flatter and flatter. Okay? That's what that means, right? Let me just talk about one more thing here, one very quick here. So using this equation we have, can you predict earnings of a person with 12 years of schooling and 10 years of labor market experience? How can we do that? Think about it. Well, you can plug it in here, right? Okay. And when you plug it in, that would be, comes out to be 7.36, right? When you calculate that equation. Does that mean the person's earning would be what? $7.36? Huh? Right. This is, remember, this is log of, or natural log of earning, right? So actual predicted earning is e to the power of 7.36, which is 1,571.84, something like that, right? So maybe this was the monthly earning, right? $1,571 and something like it. Doesn't matter, right? But make sure you understand this. When you get this number for the log of earning, you have to convert it into actual earning by taking exponent to the power of 7.36. Well, you have to understand this because we use this idea again in chapter 16 when we talk about the time series analysis, right? And we're going to use this idea again, right? So today we talked about two different log transformation, the log-log model, log-level model. If you look at this printout, this handout, actually they talk about 4 different log transformation, right? The level, which is really not a log transformation, right? Log-log, log-level, and level-log, right? So if you read this, I think you can easily understand because I've already showed you a couple of examples. So it's up to you. I mean, this level-log, I'm not really concerned about level-log, but for your own interest, you can try to understand this, right? Okay, so we're going to continue and finish this chapter on Tuesday. Have a good weekend.